So we're on page 10 of our chapter 5 note packet, where it's 5.5 counting techniques. And the whole idea is, if it's just a normal problem, 52 cards in a deck of cards, 6 sides on a die, we know how many ways things can happen. But when things start getting a lot more complicated, it's hard to know, okay, what's the total number that we're looking at? So 5-5 is a way for us to actually figure out how many ways things can occur. So objective 1 is called the multiplication rule. It says if you have 3 different colors of paint, red, blue, and green, that can be used to paint 2 different types of toy cars, a race car, a police car, how many different toys can be made? There's 2 different ways to do it. One was with a chart to show you that you have 2 types of cars and 3 colors. Do you guys agree that there's 6 different toy cars that are happening? 3 are based on the type of car, right? 3 and 3, and then the other are based on the color. You also could do a diagram, start with the paint color, red, blue, and green, and then realize each of those have 2 types of cars you can be coloring. So again, you have 6. But what if this was extended to material of a car, size of a car, price of a car? All these different options could get really big, so a chart or a diagram might not be the most practical. So what the rule is, it's actually just the multiplication rule if you look at it here. It says, if a task consists of a sequence of choices in which there are P selections for the first, Q selections for the second, R for the third, S for the fourth, T and so forth, you're just going to multiply them. So this is the number of paint colors, 3, times the number of types of toy cars, 2. What's 3 times 2? 6, okay? So when you have to pick 1 from each category, we're just going to multiply how many from each category we have. So it says an access code for a Ford security system requires 5 digits, 0 through 9. Does anyone own a Ford or did at one point where you had that keyless entry on the side? Like I grew up with a Ford Explorer. So I would just drop my keys in my car, and then I would lock the car, and I thought it was so cool. It's cool until you tell someone your code, and then you come out of your school parking lot and notice your car is gone. So what it is it's just this way to get in, or your garage code, right? We have the garage code. So how many total things do we have? We have 5 digits, right? It's kind of like our probability, right? We had to pick multiple cards or multiple people. We're picking multiple numbers to be on that code, okay? So how many different codes could we make? Like if we want to break into this car without breaking in, we just want to pick the right code. How many different codes are there if we can reuse numbers? Well, how many numbers are there on a normal number pad 0 through 9? 10. It's a trick question. You want to say 9, right? But there's 10. So when we make our code, how many options do we have for the first number? 10. But guess what, guys? We can reuse our numbers. So when I go pick that second number for my code, how many options are there? 10. And when I pick that third number for my code, you see a pattern? So really when it comes down to it, however many numbers are in your code, it's 10 to that power. So since this is a 5-digit code, it's 10 to the 5th power, or 100,000 codes. Why do we need this for probability? Because in your My Math Lab homework, this will be part A. And then part B will say, what are the odds that you pick the right code? Well, how many correct codes are there? 1. So what are the odds that you pick the correct code? 1 out of 100,000. So just break the window, right? No, I'm joking. And I just got that on recording too, so let's not share this. All right, this is not going to happen, but say we cannot reuse our numbers. What are you going to notice that happens? Well, it's still a 5-digit code. But you're going to see something happen just like when we were picking those marbles and we weren't replacing them, right? So when I go to pick that first number for my code, how many total numbers do I have to choose from? 10. But say I pick the number 1, how many numbers do I have to choose from now? 9, because 1 is ruled out, right? And then say I pick the number 3, how many numbers do I have? You're seeing a pattern, right? Since we can't reuse the numbers, every time I pick a number, it's decreasing my choices, all right? So if you have a security system where you cannot reuse numbers, it's not as secure because there's not that many more options. It's still a big chunk. What is it, 30,240 codes? So what's your odds of picking the right code there? 1 out of 30,240. Still very unlikely, but notice it's not as secure as one that has unusable. And just think of your code. That's why they say your password, the longer your password, the better. You know what I mean? How many different characters do you have to choose from? 10 to the 8th if you have to have an 8-digit number. Okay? Let's go ahead. I think this is the best example of it. Anybody watch Tiny Homes? Are you guys like HG people at all? You know what I'm talking about? Even if you don't watch it, you guys know what it is. It's like this big fad to buy a house under like 200 square feet, right? I always wondered, where does their stuff go? Like, where do their pots and pans go? Where do their outfits go, right? There's no storage in these places. So say you own a tiny home, and you only have room for 5 shirts, 3 pairs of pants, and 2 pairs of shoes. How many total outfits could you make with just those articles of clothing? Well, how many different articles or clothing are we choosing from? 3. Shirts, pants, shoes, right? When you go to pick a shirt for the day, how many total options do you have? 5. When you go to pick your pants for the day, how many total options do you have? 3. And assuming your shoes match every outfit, how many pairs of shoes do you have? 2. This blows my mind, guys. With that little amount of clothing, you actually have 30 different outfits that you can make. So you could have a different outfit for every day. Granted, one outfit would just be a difference of shoes, right? You'd be wearing the same shirt and same pants. But to me, that's still pretty remarkable that you could have that small of clothing and still have that many different outfits. Another good example, do you guys eat out ever at like Chili's or Applebee's where it's like when you're going out and there's just the 2 of you and you can pick from desserts, meals, and appetizers, you know, that kind of thing. It's the same idea. How many total different meals can you make? Well, how many appetizers do you have to choose from? Times how many entrees, times how many desserts, all right? So you're picking one from each category, you're just going to multiply. All right, so the next thing we need to get to is objective 2 with permutations and combinations. But before that, we need to learn the factorial symbol, okay? So the factorial symbol is kind of right here. He is the exclamation point. Has anybody seen the exclamation point before? Okay, and it's not like in, get it? Get it? Anybody? No? Okay. So we're not just screaming in because it's an exclamation point. It's actually a mathematical symbol, all right? And what this symbol means, it means start with that number. So whatever n is, start with that number and then multiply down. Kind of like what we were doing with our codes. We went 10, 9, 8, okay? You're going to do that. You're going to start with 10, 9, 8, and you go all the way down to 1. For purposes of this class, or just math in general, 0 factorial is always 1. I'm not too sure where the proof is in that one. And of course, 1 factorial is just 1. So say we want to do 5 factorial. What would that be, guys? That would be 5 times 4 times 3 times 2 times 1. Okay? Start with the number you have and multiply down. They get big pretty quickly, okay? They're not as big as exponential stuff, but they are pretty big. Is that 120? Yeah. But who wants to do that if I tell you guys, hey, figure out 10 factorial? Who wants to type 10, 9, 8? So what we have is we have a calculator cheat sheet for 5.5, okay? So this is just specifically for section 5.5. I don't know if anyone labels these. So this is 5.5. We can actually do factorial symbols in our calculator, which is nice, because it will save you the time from having to multiply down. How am I that far off? You got an extra one, and then you got some 2, and 2. There you go. Okay? So anytime you guys want to do a factorial symbol, you have to type that number first. So let's do it with 5. Type 5 first in your calculator. And then you'll scroll over to, you'll hit math and scroll over to PRB for probability, and you'll find the exclamation symbol. So we'll type 5, and then you hit math, scroll over to PRB. The exclamation is number 4, and you hit enter, and it figures it out for you, 120. So that's nice because if it's 10 or higher, it gets kind of tedious to actually write that. So when do you need to use factorials? Off to the side. Use when rearranging everything. Use when rearranging everything, okay? So we're going to be given a chunk of something, and everybody gets to play, everybody gets used, whatever it may be, okay? So again, in this section, I know you guys aren't as amazed as I am, but I get pretty impressed with how large these numbers get. So say you're a baseball coach and you need to make a batting order. And let's just say it's like T-ball, because batting order has a lot that goes into it, you know, who's hitting third, fourth, or whatever. So let's just say it's T-ball. There's 9 players, and everybody gets a chance to bat, right? So how many options do you have for that first player? How many options do you have to choose from? 9. But once you choose that first person on the roster to bat first, how many options do you have for the second? 8. How many do you have for the third? 7. All the way down to that 9th player. So do you guys agree that since we're playing everyone, that this is 9 factorial? You guys agree with that? Everybody on that baseball team, all 9 players, are going to get a chance to bat. Throw that in your calculator real quick and tell me what you get. 362,880 starting lineups. You just have 9 little T-ball players, and you have over 360 ways you can place them on your batting order. Does that blow anybody else's mind? The same 9 players, right? Oh, it's crazy. Okay. When else might you use this? I don't know. Anybody, any big readers? Like you have a bookshelf of books, right? How many different ways can you rearrange the books on your bookshelf? Count how many books you have. 14 on that one shelf. 14 factorial is how many different ways you can rearrange those. Say you don't read, but you like to eat. Anybody eat cereal? How many different cereal boxes you have on your shelf? Right? 14 factorial. That's how many different ways you can arrange those cereal boxes. Because I'm sure that's what you guys think about. How many ways can I rearrange these boxes on my shelf here? Okay. We don't use this a whole lot in this class, but it is good to know whenever you're playing, rearranging, using everything, it's going to be the factorial. What we really need the factorial symbol for is an objective 2, our permutations and combinations. Guys, this was one place, like I was a little math geek throughout my whole childhood and college career. This was the one section where I really, really struggled, and I blame it on my teacher. And I know it sounds bad, because you shouldn't blame your teacher, right? But he just did not make the difference. I did not see what he was talking about. So I'm going to try my darnest to make sure you see where I struggled, and I hopefully can correct that. So what is a permutation? It is when you're ordering an arrangement, but only of a small chunk of objects, okay? So you have our objects chosen from N. What is N always? Your sample size. So that's true, still true. So we learned it in chapter 1. We're still using N for our sample size. R, though, is the smaller selection. So instead of rearranging all the books on my bookshelf, maybe I'm just choosing 3 of them, and I'm curious about how 3 of them can be arranged, all right? So you're choosing a few from many. Few from many. The symbol they use is this big P. Little n, how many you're choosing from, is always in front. Little r, how many you're choosing, is in back. It represents the total permutations that we can do, okay? What are the 3 main factors? 1, they have to be distinct, meaning the books cannot be the same. Like I can't have 2 algebra books or 2 stats books. They have to be different, okay? We have distincts. We cannot be repeated. So basically once you're chosen, you can't be chosen again. So it's like without replacement. Order is important, is the number 1 thing. I just could not get this through my head. He could not specify it. Order is important. It's the same thing as something special is occurring. I can't write today. Something special is occurring. And what do I mean by that? You being chosen first is different than you being chosen 5th, okay? Because something special is happening. Either you're getting a special title or a special trophy or a special color. You being chosen first is different than you being chosen 5th, aka the order is important in which you're chosen, okay? And I could not get that. He might have been saying it and I just couldn't get it. So how do we use this? This formula, I'm not going to worry about the proof. But if you were doing it by hand, you put the total number factorial on top and kind of the complement, the opposite on the bottom. But guess what our calculator can do? permutations, okay? So when we go to do this, I'm not going to even worry about using the formula. I'm going to use my calculator. When you go to do your calculator, you have to type your n first, 10. So go ahead and get your calculator out. So I'm going to type my 10. Then you go to math and you scroll over to PRB, and notice number 2 has the NPR. And then you choose your second, your R, which is 2. And you get 90 there. Okay, is that what you guys got? So if you wanted to do the formula, you could. It would be 10 factorial over 8 factorial. Well, you'd start 10, 9, but the 8s would cancel out from there on. Okay? I'm not worried about that. I'm more worried about these. How do we know when we use permutations? Well, one, you're choosing a few from many, but then something special is happening. Okay? So let's look at this first example. In a race, there are 8 competitors. How many ways can the competitors finish in first, second, and third place? Do you guys agree that we're choosing a few from many? We're just choosing first, second, and third, a few from many, the total number of competitors. So that's going to narrow it down to either permutations or combinations. Why is this a permutation? Bless you. Do you guys agree that you finishing first is different than you finishing third? Right? You get a total different medal, a total different place in on the trophy stand or whatever, okay? So guys, what is this? This is 8 perm 3. This is 8 perm 3. 8 because we're choosing 8 total competitors. 3 because we're worried about first, second, and third place. So in your calculator, you're going to type 8, hit math, scroll over to probability, choose 2, type 3, and what do you guys get? 336 ways. Again, that blows my mind. On a track field, you only have 8 lanes, and you're only worried about the top 3 finishers, and you have over 300 ways the top 3 finishers can finish out of 8 runners. The next example, there are 12 members on a board. How many ways can a vice president, president, treasurer, and secretary be assigned? Do you guys agree that we're choosing a few from many, right? So how many are we choosing from? 12. How many are we worried about choosing? 1, 2, 3, 4. Why is order important? Because you being chosen as president is different than you being chosen as secretary, right? There's something specific happening to you. You're getting a title. So 12 perm 4, if you guys do this, again, it blows my mind. There's only 12 people on the board. We're only worried about 4 different titles, and you have nearly 12,000 ways on that tiny little board to have a president, vice president, treasurer, and secretary. Okay? So this next part, guys, is where I struggle. Okay? I was introduced to this. I'm like, okay, sure. Permutations, a few from many. Talking to my calculator, I got it. Then he introduced combinations. I'm like, what the heck? How are these any different? Like, how? I don't understand. I don't see the difference here. So combinations, if you read the definition for combinations, they're basically identical. There's just one key thing that's different. So combinations, again, a collection without regard to order. And so that's the key thing. We don't care about the order. We're still choosing from our sample size of n. We're still choosing R. That's how many we're choosing. They have to be distinct, so I have to know the difference between them. They can't be repeated. But order is not important. If you're chosen first, it's no different than if you were chosen fourth, okay? Order is not important. So once you're chosen, nothing special is happening. Once chosen, nothing special. Because to me, being chosen special, right? So being chosen special, but once you're chosen, you're not getting a title, you're not getting a trophy, you're just one of the 4 that got picked. No big deal, okay? So there's not going to be as many combinations because they're not going to be as distinctive as, okay, president, vice president, they're just 2 people picked. So what we do is in the formula, we divide out a little bit just to get rid of those repetitiveness. But again, guess what our calculator does? Combinations, all right? So it's very similar where you're going to type 7 first. You'll hit math, you scroll over to probability, but now you'll go down to 3 to combinations. And you'll notice these don't grow as quickly as the other ones. So what do you guys get when you do 7 combo 4? 35. All right. Again, I'm not so worried with the calculation as I am when do you know to use it, okay? So when we read these next two things, please tell me that you can notice the difference than those other two things we just did on the bottom of page 11. How many subcommittees of 9 can be made from a committee of 21? So we're still choosing a few, right, from many. So it's still either a permutation or combination, but when you get chosen to be on the subcommittee, is anything happening to you? No. You're not getting a title, you're not getting an award, nothing. So this is just 21 combo 9. Okay? How many ways can I just pick 9 people out of 21? Still blows my mind how many you can do. Guys, if you put this in your calculator, you get 293,930 subcommittees. So we have 22 people in this class. So if I did 22 choose 9, we'd even have more subcommittees of just picking 9 of you. So just how many ways can you pick 9 people from 21? Nearly 300,000 ways you can do that. The second example, how many different 2-topping pizzas can be made from 9 toppings? Are we choosing a few from many? Yeah, but does it matter how we choose them? No, we're throwing them on our pizza, right? So this is going to be a combination. How many total are we choosing from? 9, and how many are we worried about choosing? 2. So I know like Domino's and stuff, we have way more than 9 toppings, but if you just had a restaurant where you just had 9 toppings, you could make 36 different types of pizzas with just 9 toppings and 2-topping pizzas.